Good afternoon. Welcome back. This is part two on Rheem, the modulating gas furnaces, both service, installation, and troubleshooting. So we will get right into it. We left off last time at the sequence of operations. So there actually is a pretty unique um, sequence of operations with the 97 and 98 modulating gas furnaces. They have what they call a calibration sequence. You'll see here at the bottom, the calibration occurs on the original R97V, the USA. The calibration occurs every 100 heat calls. On the newer, the R97 KSA and the R98V USA, the calibration occurs every 1,000 heat calls. So what the calibration circuit sequence is, it learns how to match the RPMs of the inducer motor to make or break the pressure switches. So the switches used in the 98V and 97 KSA have calibrated make close contact points as opposed to the calibrated break contact points with the 97 USA. All make switches will have an M located on the switch, and the break switches will have a B on the switch. Like I say, the whole process of this is to calibrate the inducer RPMs based upon, and it's a learned process to calibrate the low pressure switch, the mid, and the high fire. So when you're doing this, it'll tell us here in a minute as well, but when you're doing this, you have both doors on, just like it's in normal operation. If you do leave the door off during the calibration sequence and you put the door back on, then it's going to completely change the dynamics of it, because it's going to learn with the door off, what those points are, and if you put the door back on, now it's not going to calibrate correctly. So during an initial startup or heat call, if the condensate trap has not been primed already, you will get a water sense fault 59 during the warm calibration. The gas valve circuit will be energized, and the calibration sequence will begin again. You'll know when you're in calibration sequence, the 7-segment display will display a CL, and that's for calibration. And there's two sequences of the calibration. One is a cold calibration. That's where it's running through the sequence, but it's not actually firing. So during the cold calibration for low fire pressure switch, the control board will energize the inducer at a low starting RPM and increase the motor until the low pressure switch closes. At this point, the IFC notes that RPM, saves that in the memory, adds the value to the predetermined value, and save that result in the furnace memory. Next, it'll go into the mid pressure switch. It will continue to increase the RPM until the mid pressure switch closes. At this point, the IFC notes that RPM value, adds that to the predetermined value, and saves the result into the furnace memory. Next step in the cold calibration, it will keep continuing to increase the RPM until the high pressure switch closes. At this point, the IFC notes that inducer RPM value, adds that to the predetermined value, and saves that into the memory. After that, the cold calibration is complete. Immediately following the cold calibration, the IFC control board begins a 30-second pre-purge period and up to a 7-second trough for ignition. Following burner ignition, the furnace will begin a 2-minute warm-up period. Following the warm-up period, the IFC will determine the necessary RPM that corresponds to open and close points of the high, the mid, and low pressure switches. So during warm calibration, the IFC steadily reduces the RPM until the pressure switch opens. So once it recommends that, it will note that, it'll add that to the predetermined value, save that into the memory. Now your high fire pressure switch is going to be the RPMs for 70 to 100% firing rates. The mid-level, there again, it's going to keep on reducing the inducer motor. The gas valve output is reduced to 65%. It keeps reducing until that mid-pressure switch opens. At that point, the IFC notes the RPM value, saves that to the memory, and this value is used to target the RPMs between 50 and 65% firing rates. Once the mid calibration is complete, it's going to go into the low calibration. For the low pressure switch, it's going to keep reducing until the low pressure switch closes. Once that pressure switch opens, it will save that value, and this particular value will be used as a target RPM for 40% firing rates. That's your low. After that, the warm calibration is complete. If you have a call for heat during this cycle, it will not be interrupted. You cannot stop or override the calibration sequence. So generally speaking, whenever you first power up the furnace, it's going to go through this calibration sequence. And you just have to kind of let it just do its thing. Not much you can do to stop it. But if you have a call for heat, as soon as it finishes warm calibration, it'll go right into your heat call for you. So the heating call sequence, upon proving successful flame, the IFC continues in this order. If the calibration cycle is active, the IFC proceeds to the warm calibration cycle following the 2-minute warm-up period. If the calibration cycle is not active, a 2-minute warm-up period will occur. The firing rate will be set at 100% for the first 22 seconds of the warm-up period, and then the IFC will accept the thermostat demand. So I first came across one of these on a Linux. It was a 98 something, and it just kind of starts up on its own, and the inducer motor is running up and down, up and down. There was no manual to know what was going on with the Linux, but what it was actually doing was actually calibrating. So the calibration sequence can take anywhere from 7 to 9 minutes, depending. Let me go back here. The blower on delay. The IFC energizes the main blower 22 seconds after the start of the ignition trial. During the 2-minute warm-up period, the IFC runs the inducer motor at an RPM determined during the cold calibration sequence for the low, the mid, and high fire pressure switches. When the warm-up period ends, the IFC will run the inducer motor at the RPM determined during the warm calibration sequence, and the IFC proceeds to steady state heat mode. If you're in steady state heat mode, the blower CFM values will be a function of the current firing rate. The selection of this is either in comfort or efficiency modes. Dip switch SW18, or if you're using a communicating EcoNet, that can also be set up in the EcoNet thermostat as well. Inducer post-purge, after the gas valve is de-energized, the inducer will continue to run for 28 seconds at mid-fire RPM. After that, the blower off delay will begin after the gas valve is de-energized, and when detected error conditions that have been cleared require the blower to be energized and then de-energized. There is a usable selectable dip switch, SW17, or for communicating system, you change that in the EcoNet Smart Thermostat. The blower off delay will run at the same CFM demand that the blower was at when the gas valve was de-energized, or at the CFM matching 100% firing rate if the blower was off. If a compressor call occurs during the blower off delay, the IFC will immediately switch the blower output CFM to whichever CFM is greater, cooling CFM or heating CFM until the end of the blower off delay period. At the end of the blower off delay, the blower CFM shall be set to cool or HP CFM setting. So they do have some, like I say, some sort of unique features. So you really don't want to turn to, break your power, your 120 volt power, unless you have to, because conceivably every time you completely break your power, you can have to wait for a calibration sequence. So you have your normal operation codes. So if you walk up to it, once again, as with the 90s and the 96B, 0 means you're in standby mode, no faults present, and no call from the thermostat. If you have a capital H or a lowercase h, you're in heat mode. Capitals for high stage, lowercase is for low stage. Cooling, same thing, capital C or lowercase c is cooling mode. Capital C is for high, lowercase is for C for low stage. And it will determine and indicate when it's in heat pump as well. So if you're in heat pump heating mode, it'll say capital HP or lowercase HP. If you're just in continuous fan, you will have an F. And if you are in defrost mode with a heat pump, you will see a DF on there. That indicates that you are in defrost mode. You also have a capital CD or lowercase CD. That's when cooling is taking place in dehumidification mode. So it's pretty robust in telling you what to expect and what the operation is. So if you just take the time, look at the 7-segment display, you can learn basically what mode it's in, any faults that are present. And some of the fault codes we see here, I won't go through every single one, but I'll hit some high points here. A D1 indicates there's no model data. So possibly your model data card is loose or corrupted or damaged in some fashion. So if you don't have a model data, it doesn't know really what's going on. So you can expect no operation with a corrupted no model data card. The solution is to replace the missing model data card. If it's corrupted, there again, same thing. Order the model data card specific by the model and serial number of the furnace you're using. Note, furnace power must be cycled off, then on again after replacing the card, or the model data card will not be read. We have another one here. A D4 is no valid model data on your card. This is a non-critical fault. It will still operate in most modes. Expected operation, since model from the data card cannot be used, it will still proceed as normal, but you'll get the D4 fault. The solution is to remove the model data card and replace with the original or the correct replacement. Now, in red down here at the bottom, this is huge. Never replace the model data card of a furnace with a model data card from another furnace or component, e.g. air handler, condenser, heat pump. Doing so could result in improper operation of the blower, which may cause damage to the heat exchanger. Usually, if you use the incorrect model data card, it's going to give you an error code and it won't even work. But people try. if you do end up using, sometimes you do use a different card, you'll get a horsepower conflict on model data card. This is a non-critical fault. Two possible causes. The blower motor was recently replaced with the wrong horsepower, or the model data card or furnace control has been replaced and the wrong card was used. Solution, obviously determine if you have the correct motor and the proper card. Once again, because it's been tried more than a few times, never use another model data card from another furnace to substitute. Let's see here. 66. This is a big one. There again, we're dealing with an ECM motor. If you turn the furnace on and you're looking at your 7-segment display, you may very well get a 66 that comes on immediately. What it's trying to tell you something. It says it's a non-critical fault. Everything will still work, but it's indicating that the furnace, the blower, is operating at the highest RPM or torque that the specifications allow. So it's telling your static pressure, whether it's on your supply side or your return side. Had one where they had half the vents cut off in their house, and this 66 popped up. Now I knew the duct system, so I knew the static pressure was fine. So when we got this 66 code, I knew something was wrong. So we just had to kind of dig in a little bit, and they had shut all the vents on the second floor. Expected operation, if you get the 66, it will actually disappear after a short period of time. That 66 is just kind of a tool to tell you. If you're using an EcoNet thermostat, well, it will also kick back on your EcoNet as a 60. It'll give you a 66 blower cutback fault. So once you get the 66 for the first 3 minutes, it will show the 66, then it will disappear. Over time, if you get the 66, what you're going to notice automatically is sound. It's going to be loud. It's going to be obtrusive. That's obvious, generally speaking. Blower operation will continue. Over time, it will be compromised, but it will continue to run. As a byproduct of that, the customer is generally going to complain of noise. It's not going to be as comfortable as they expect. And eventually you're going to destroy the motor. They'll cause the module to fail. This is a huge one. Okay, this is a big one here too. 58. This describes the water circuits. In this case here, it's a water circuit open. This is a critical fault. The furnace will not operate in heat modes, but it will operate in cooling. So if you have a water circuit that's open, you have 3 points of contact for your water circuits. You have your 2 switches, and you also have the IFC control board. Best thing to do on those, because it's determining that they're open. Take all connections loose, inspect your connections, check for corrosion or damage on the 2-pin connectors. If everything looks good, there's no water in there or anything else, go ahead and snap those all back in and see if the fault disappears. If it disappears, you just had a loose connection. I have seen a couple of them where they get moisture in the connectors and corrode, even though they're connected good and they're snapped in good, they're just not sending that circuit back. In that case, they had to get a new wiring harness. Now here's your water sensed. You'll eventually get this at some point with all 90% furnaces from Rheem. If it's brand new or it's a dry trap, you'll get the 59 error code with the self-priming feature. This is a critical fault. The furnace will not operate in any gas heat mode, but it will still operate in cooling and fan. So as far as it's concerned, the IFC has detected current flowing through the pins 1 and 2 of generally speaking, the lowest water sensor. So it's not, as we discussed in the first one, it's a little needle there. So if you just have water splashing on it, it's not going to trigger this sense. If it's a true water sense situation, the water has to come up and basically sit in that sensor for at least 10 seconds. If it's anything less than 10 seconds, you won't get the water sensed. So it truly did have to trip some sensor of some sort. Also, you can get, if you have PVC shavings, I've seen that before, get back in the secondary, the collector box. If it's such a buildup in there, it can actually create the short or create the ground from the water sensor to the secondary exchanger. So sometimes pull those out, look in there, and kind of, take a piece of thermostat wire and make sure there's nothing behind there. Let's see here. Code 77, you have a no gas valve feedback signal. This is a critical fault. The furnace will not operate in gas heat modes of any kind. It will still work in cooling. So we have some videos here, which I'll show here in a few minutes on different ways to diagnose and troubleshoot various aspects here. So in this case here, if you have no feedback signal, could be bad wiring to the gas valve, could be a bad valve, could be a bad control board. And the number 93, the internal control fault detected. This is a critical fault. Occasionally you'll see this. Generally speaking, it's found to be a board. Basically, it's a fault within the internal microprocessor. Had a couple of them where you could actually switch the low voltage transformer leads, and that seemed to fix it. That was into the phasing that was causing that. There we go. So as you can see, there's quite a different, quite a list of fault codes. The control board, the IFC control board, will give you a lettered or numbered fault on the 7-segment display. If you're using the EcoNet thermostat, it'll actually give you a legible fault code as well as a EcoNet specific fault code. So if you have to ever replace the circuit board, the control board, the model data card must be removed from the original control. There is a zip tie there. It's tethered there for a reason. So you have to take it out in order to change the board. Failure to save and connect the original data card properly to the replacement board may result in no operation or undesired operation. When replacing the furnace control, be sure to match the dip switch settings of the original board. If you're using the EcoNet, you don't have to worry about that. Do not cut the plastic wire tie as a tether that's attached to the model data card. Doing so will defeat the purpose of retaining the model data card. We've seen this a few times actually, where guys just cut the zip tie. They'll take the whole board out. They chuck the board or damage it in some fashion. They're looking at getting a new card. Okay, I'm going to jump ahead here to talk about the EcoNet. They have a nice little simulator here in case you haven't seen the thermostat yet. Here we go. That's the EcoNet Smart Thermostat. That's the most updated version of this. A couple of features on this. It's very intuitive, easy to walk through. Even if you don't have a manual, just fiddling with it a little bit, you can learn all the functions. The top part here says Rheem. If you click that, this is helpful for the customer and also making sure you get the business back. Enter your phone number, contractor name, company name, email. If the customer's having any kind of Wi-Fi or app support, this number right here is who they want to call. If you're there on site, you can call them, but they'll really want to end up speaking to the customer. So you have your home and away feature here. This little triangle here is telling us that we have an error of some sort. Here's our Wi-Fi. Our water droplet here we are able to set up enable dehumidification, dehumidify set point. You can also set up overcooling. And then you have this where it says dehumidify drain timer. This is factory set for 5 minutes. So what's that is designed, that can be increased quite a bit actually. Basically at the end of every cycle, your blower is going to turn off for 5 minutes. There again, you can increase this 7, 10, 15, whatever you want to. The purpose behind this is those new coils, they're so much bigger, they're so much denser. So once the cooling cycle is over, it holds quite a bit of water. So if your fan's running all the time, you can take some of that moisture and put it right back into the airstream again. So this dehumidify drain timer is set for 5 minutes for the fan to shut off and give it 5 minutes for that moisture to drain. You can turn it off if you want to, but if you were to get a complaint that, after every air conditioning cycle, my fan turns off, then it magically turns back on in a few minutes, that's the problem. So we can set up our humidification. We can enable it here. We can set our humidity set point. We can humidify during heat, even cool if you wanted to, and heat and fan. You can set up your smart control. And then you can also say humidify with fan. And down here you can pick your actual speeds. I want low speed with humidification, medium, whatever speed that you'd like. Go into your settings here. If you would have a EcoNet water heater or pool heater hooked up, you can also control it from here. We'll go into service over here, so we know there's an error code there. Excuse me. It's telling us, so here it is, A004. It's telling us air source not detected. This furnace is not detecting the furnace or air handler. We can go back and look at the history. So we had a restricted airflow detected, possible frozen coil, 240 volts missing. Probably somebody pulled the disconnect. And it will store 10 faults. It will kind of keep scrolling through there. So anytime you come up on one of these and you're even on a tune-up, check your history first, because it will give you a roadmap on what to look for. Alerts, you can turn your service call, say every 6 months. Air filter, it will do an automatic air filter check every day at 9 a.m. You can change that time if you need to, but every day it's going to check that. So it's going to set a baseline for your static pressure. So if, for instance, you have a really dirty filter, it's going to tell you to change your filter. If you have, let's say, half of your vents shut off, it's also going to tell you, it's not going to know the difference. It's just going to notice the static pressure is really high, and it's going to give you an air filter reminder. If you had a humidifier hooked up, You can turn it on for reminders as well as UV lights. If you go to the equipment information, with the original furnace board and model and data card, same with the outdoor unit boards and model data cards. In this case here, it tells us our version of the software. They're constantly revising that. In this case here, our model number was R98V. It even gives us our serial number, furnace software version. We know what that is. In this case here, we have a RP20 outdoor unit with serial number and our outdoor version. If you need support, there again, pop that up. It'll bring up all your information. Schedule is easy enough to do. You can do it here or on the app. Now this is one I really like here, your furnace status, because I'll keep talking about static pressure. So you have the furnace running, or let's say air conditioners running. You can go over here to the furnace and check right here. Obviously, air conditioning is your highest RPMs, so you can actually look right here and see what your static pressure is. And this is actually pretty accurate. If I individually test it against this, it's only going to be a point or two off. So it will give you your static pressure, give you your cycle counts here, give you your capacity, your CFM, your RPM. If you're using supply temperatures, supply or return air temperatures sensors, it'll tell you that. Same with AC heat pump. So if you have an inverter system, this is where it gets real cool. You can actually check your inverter speed. It'll tell you what your RPMs are, crankcase heater, superheat, suction line temp, and suction line pressure. If you have an air handler, there again, if it's an RHMV, it'll tell you what your static pressure is. First thing I do when I go on a site visit is check the static pressure, because that's going to tell you a lot of what's going on with the system, just that one reading. So if we go into our basic here, we can follow a schedule. If we don't want to follow a schedule, just turn this off. It's even got an alarm beep, screen lock, Fahrenheit, Celsius, override, auto changeover, your dead band. You can set up a temperature offset if you wanted to, as well as a relative humidity offset. You have the option to use the internal sensor of the thermostat, or you can actually set up for a remote sensor. It has proximity sensing as well as smooth and arrival enabled. And you can enable the backlight. Over here in the fan, you can go over here to the fan settings. This is going to be your constant continuous fan. So you can say I want low, medium, low. You can change that up and down from there to set your continuous fan settings. Now, if you go to the installer menu here, so if we're going to set up a furnace, we talked about the dip switches earlier. So in this case here, if we have an R97 KSA, we need to go in here and highlight this one, change it to downflow. So our 7-segment display rotates. Here's our blower off delay, high heat airflow adjust, low heat. Our auxiliary 1 and 2, we can configure those. If we're using a smoke detector, float switch, whatever you have. And here's where you put in your filter type, fuel, and elevation. If you have a, in this case here, there is no outdoor unit selection. If it's a communicating system, it'll say EcoNet locked. Or if it's a non-communicating, you can go in here and configure it to be non-communicating, AC, heat pump, what have you. Thermostat here, right here, it says filter check hour every day at 9 a.m. I've never heard anybody complain about or even notice the filter check. But if you wanted to, you could put that in the middle of the night and nobody would notice, no any different. Air handler. So if you have electric heat, you want to put that in here. Your EXB superheat offset, you don't really need to adjust that for anything. And there again, you can set up your auxiliary 1 and 2 safeties. So that's pretty much it with this. Now, you also have a feature, which this demo doesn't show us. But if we go into settings normally, we'll have an option down here to say checkout or test mode. So we can go in here and say if we're having a 98V or 97V, we can go into test mode. We can click that. We can physically from the thermostat here, instead of doing dip switches, we can from the thermostat here, we can set it in high heat, 100% capacity. Then we can also go in and set it at low heat, and then we can set our pressures and check our pressures that way. Otherwise, you have to basically jump R and W. You know, you're taking your door on and off, setting dip switches, which is fine. But you could run into a calibration sequence every time you break power. So that's something to be aware of. Also, if you're using the EcoNet and you have a communicating outdoor unit, you'll also have the option to go into test mode here as well to test your outdoor unit. If it's a two-stage AC, you can pick first stage, second stage. If it's an inverter, you can pick low, medium, or high. Or the newest one says charge heat, charge cool. So that's going to be your highest setting. So it is a good idea to have the EcoNet. It's pretty user-friendly, intuitive thermostat. It's got the Wi-Fi built into it. My opinion is pretty easy to navigate. Never heard anybody really complain about it, per se. So let me get back over here. There we go. Okay. Well, I'll tell you what, it's 3:37. Let's take a 10-minute break here. We'll start back up and we'll go through some of the videos. Actually, pretty nice troubleshooting videos from Rheem. It'll actually show us specific step-by-step troubleshooting on some components that we don't normally do every day or necessarily know how to test accurately. So we'll come back here at 3:48. Okay, we'll get right back to the videos now. These are step-by-step videos as part of the video library from Rheem regarding their 97V and 98V gas furnaces. So we'll go through a few of these here, kind of step-by-step, play the videos and see. They do a pretty good job of explaining how to do the different tests. So we'll go through gas pressure measurements and setup first. Outlet manifold gas pressure measurement adjustment. Rate adjustment is a combination of selecting the right orifice based on the heat value and altitude. The outlet manifold pressure on this modulating furnace is capable of being adjusted at the maximum firing rate and at the minimum firing rate using the same adjustment. Note, not attempt to adjust the outlet manifold pressure at intermediate
gas manual shutoff valve located outside the furnace to the closed position. Step 4. Important. Be sure that the gas manual shutoff valve located outside the furnace has been in the closed position for at least 5 minutes. Remove the outlet manifold pressure tap plug and the gas valve. Step 5. Install field supply pressure tap to the outlet manifold tap. Connect the positive pressure hose from a manometer to the pressure tap. Step 6. Go to the Ethernet smart thermostat and set the furnace to operate at 100% fire rate. If 24-volt legacy control is being used, set dip switch SW10 to the off position and dip switch SW11 to the on position. This will force the furnace to operate at the maximum fire rate, 100% with volume. Step 7. Replace the blower compartment door. Step 8. Turn gas manual shutoff valve located outside the furnace to the open position. Step 9. Connect furnace electrical power supply. Step 10. After ignition, allow furnace to operate in complete pressure switch calibration before checking maximum firing rate outlet manifold pressure. Note, the manifold gas pressure is 2.5 inch water column plus or minus zero point 0.3 for natural gas or 10.0 inches water column plus or minus zero point 0.5 for LP gas. Step 11. To adjust the outlet manifold pressure, insert a small slotted screwdriver into the opening at the top of the valve. The adjustment wheel is shift from the factory in the nominal position, noted as position A on the wheel. The wheel can be adjusted 4 full revolutions, 64 clicks clockwise to increase manifold pressure, or 4 revolutions or 64 clicks counterclockwise to decrease manifold pressure. Each click is a very minimal adjustment. Several clicks may be required to adjust manifold pressure to the necessary 3.5 inches water column natural gas or 10.0 inches water column LP for high fire. Wait 10 seconds following each click before progressing to the next click. Verify the new manifold pressure following each adjustment. Adjusting the valve too quickly will cause the valve to stop responding. If this happens, turn the adjustment wheel back to where the wheel stopped responding and begin adjusting again. For example, if the adjustment resulted in 3 rapid clicks, turn the adjustment wheel back to 3 clicks. You may also disconnect electrical power to the furnace for 30 seconds, then connect furnace electrical power to and adjust. Use the marking on the wheel as a guide. The adjustment wheel will not stop rotating when the valve outlet pressure reaches its maximum or minimum value. Instead, the wheel can be rotated further, but no further adjustment of the outlet pressure will be made. Once the maximum adjustment, high or low, is reached, the wheel can be turned in the opposite direction, and this will cause the pressure to also move in the opposite direction. The first click in the opposite direction will cause a pressure change in the opposite direction, even if the maximum adjustment in the dual direction is finished by several clicks. If power to the furnace, and therefore the gas valve, has been interrupted, the adjustment wheel turns while the power is off, the outlet pressure of the valve will not be adjusted and will remain the same and will be reassigned to the wheel selection. Step 12. Repeat steps 10 and 11 if necessary. Step 13. Once high fire manifold pressure has been adjusted, slide the gas valve on-off switch to the off position. Allow the indoor blower to complete off delay. Step 14. Disconnect electrical power to the furnace. Remove the blower door. Step 15. Slide the gas valve on-off switch to the on position.
That's the setup for the maximum fire rate setting. We'll go over to do the minimum.
Set dip switch SW10 on position and dip switch SW11 to the off position. This will force the furnace to operate at the firing rate 40% volume. Step 2. Place the blower compartment door. Step 3. Connect furnace electrical power supply. Step 4. After further ignition allow furnace to operate complete pressure switch calibration before checking minimum firing rate outlet manifold pressure. Note, manifold gas pressure is A 0.56 water column plus or minus zero point 0.1 maximum gas, or B 1.60 water column plus or minus zero point 0.2 gas. Step 5. Adjust the outlet manifold pressure. Insert a small slotted screwdriver opening at the top of the valve. The adjustment wheel is shift from the factory nominal position in order to test A on the wheel. The wheel can be adjusted 4 full revolutions of 64 clicks clockwise to increase manifold pressure, or 4 revolutions of 64 clicks counterclockwise to decrease manifold pressure. Each click is a very minimal adjustment, and several clicks may be required to adjust the manifold pressure to the necessary 0.56 water column maximum gas or 1.60 water column for low fire. Recommend using a digital manometer capable of reading decimal places. Each click adjustment at minimum firing can result in manifold pressure change 0.100. Wait 10 seconds following each click before progressing to the next click. Verify the new manifold pressure following each adjustment. Adjusting the valve too quickly will cause the valve to stop responding. This happens during the adjustment wheel back to where the wheel stopped responding and begin adjusting again. For example, if the adjustment wheel is back in place, turn the adjustment wheel back. You may also disconnect electrical power to the furnace for 30 seconds, then connect furnace electrical power and adjust. Use the marking on the wheel as a guide. The adjustment wheel will not stop rotating when the valve outlet pressure reaches its maximum or minimum value. Instead, the wheel can be rotated further, but no further adjustment to the outlet pressure will be made. Once the maximum adjustment, high or low, the wheel can be turned in an opposite direction, and this will cause the pressure to also move in the opposite direction. The first click in the opposite direction will cause a pressure change in the opposite direction, even if the maximum adjustment in the original direction has been exceeded by several clicks. If power to the furnace, and therefore the gas valve, has been interrupted and the adjustment wheel turned while power is off, the outlet pressure of the valve will not be adjusted and will remain the same and will be reassigned to the new wheel selection. Step 6. Repeat steps 4 and 5 if necessary. Step 7. Once low fire manifold pressure has been adjusted, slide the gas valve on-off switch to the off position. Allow the indoor blower to complete off delay. Step 8. Disconnect electrical power to the furnace. Remove the blower door. Step 9. Remove the jumper across R and W1 to remove the heat coil. Step 10. Reconnect thermostat wires. There should be no call for heat present at the thermostat. Step 11. Turn gas manual shutoff valve located outside the furnace to the closed position. Step 12. Remove manifold pressure cap. Replace and tighten manifold cap plug. Step 13. Slide gas valve on-off switch to the on position. Step 14. Turn gas manual shutoff valve to the open position. Check for gas leaks using an approved leak detector. Do not use a flame of any kind to check for leaks. Repair any leaks before continuing with furnace adjustments.
That's the step-by-step to do both the high pressure and the low pressure gas settings. It did say, and it is very important that number one, that you check them. They're supposed to be fired from the factory, but that does not mean that they're going to be perfect. So you want to make sure you set your high pressure first, then set your low pressure. If you get those two set correctly, everything else will modulate appropriately. I'm going to go down here and show you the LP because it is a different conversion for the LP. So we'll show you the LP conversion video next.
LP conversion, kit Installation. Step 1. Turn off power to the unit and disconnect the gas line and the union ahead of the combination gas valve. Step 2. Remove the burner compartment access door. Step 3. Disconnect the wires from the gas valve and remove the screws that attach the manifold, and then remove from assembly. Step 4. Follow the detailed instructions on the LP conversion kit to convert the gas valve to LP. Convert the gas valve from natural gas to LP by removing the NAT sticker and applying the supplied jumper on the receptacle located beneath the label. Make sure that both prongs of receptacle engage the jumper. Step 5. Remove the burner orifices from the manifold and replace with the supplied LP orifices. Step 6. Note, to convert the stepper-controlled modulating gas valve, a jumper is required to connect the two pins inside the jumper well. It is possible to install the jumper such that the pins are not connected. This is incorrect. The jumper must connect the pins together inside the jumper well. This can be confirmed by visual inspection and by verifying proper manifold pressure high fire 100% after the jumper is installed. Manifold pressure should always be checked when converting the furnace for LP operation. The jumper well is located next to the adjustment well with the plus and minus text and two-headed arrow, and will be covered by a sticker or label. To convert to LP, the label over the jumper well will need to be removed. Note, 1.10 millimeter orifices provided in the kit are used at all altitudes. These orifices comply with the 2% derate requirements due to the natural derate related to lower barometric pressure. Note, use a pipe compound resistant to the action of liquefied petroleum gases in all threaded pipe connections. Step 7. Reinstall the manifold assembly by reversing the removal process. Step 8. Plug the wires into the gas valve. Step 9. Install the tapped gas nipple supplied with the kit into the inlet of the gas valve. Be sure to apply pipe dope or Teflon tape. After tightening the gas nipple, the tapped hole in the nipple should be in the horizontal position. Step 10. Install the inlet pressure switch into the tapped hole. Be sure to apply pipe dope or Teflon tape. After tightening, the terminals on the inlet pressure switch should be facing down towards the blower shelf. Step 11. Remove the connection in the white wire going to the gas valve. Plug the 1/4-inch female terminal from the gas valve onto the terminal on the inlet pressure switch. Using the supplied jumper wire, connect the remaining 1/4-inch male terminal on the white wire to the inlet pressure switch. Step 12. Reconnect the gas supply line to the furnace. Step 13. Turn on the gas supply and electrical supply. Step 14. Check unit thoroughly for gas leaks with soap and water, not with a flame. Step 15. Follow lighting instructions to put the furnace into operation. Step 16. Operate the thermostat to check unit operation for ignition and extinction characteristics. Step 17. Manifold gas pressure must be adjusted to 10 inches water column after valve conversion to LP gas with furnace in operation and proper gas supply pressure. See the rating plate. The gas supply line pressure should be between 11 inches and 13 inches water column at the appliance. Step 18. Note, the igniter wire must not be routed any closer than 1 inch from the gas valve. Otherwise, noise from the spark igniter wire could reset the valve during ignition trial, resulting in loss of heat. Completing conversion. Step 1. Using a ballpoint indelible pen, record the following information on label 92-18153-05 provided in this kit. A. Date of conversion. B. Installer's name, address, and telephone number. C. Burner orifice size. Step 2. Place completed conversion label next to the rating plate. Step 3. Install the burner compartment access door.
Okay, we'll go on to the gas valve communication test. As we discussed in the first section, it's a 24-volt modulating gas valve, but it also has two 24-volt terminals as well as a ground, and then two communication wires. The communication wires, that's what controls the modulation point. Your 24 volt actually engages the valve. So there's a pretty simple way to test this, and this video will show that for us.
Gas valve communication test. Step 1. Access the circuit board by removing the blower door and temporarily depressing the door switch. Power will be restored. Step 2. Check for DC voltage between the transmit and ground pins at the integrated control board, purple and green wires. If 3 to 5.5 volts DC is present, the board is transmitting. If the voltage is not present and the board is energized, replace the control board. If voltage is present, continue to the next step. Step 3. Check for the transmission signal at the gas valve, purple and green wires. If the transmit signal is present, the gas valve is receiving information from the control board. If voltage is not present, there is a break in the wiring between the gas valve and the furnace integrated control board. Repair the wiring. If the transmit signal is present at the gas valve, continue to the next step. Step 4. Check for DC voltage between the receive and ground pins at the control board, gray and green wires. If 3 to 5.5 volts DC is present, the board is receiving communication from the gas valve. If the voltage is not present, check for transmission voltage at the gas valve pins, gray and green wires. If voltage is present, the wiring is open between the gas valve and the integrated control board. If voltage is not present, replace the gas valve. Step 5. When testing is complete, release the door switch and reinstall the furnace blower door.
Now we'll proceed to the 24 volt gas valve test.
Gas valve 24 volt test. Step 1. Shut off power to the furnace and ensure the gas valve on-off switch is in the on position. Shut off the gas supply to the furnace. Step 2. Install a gas manometer onto the inlet pressure port plug on the gas valve and turn on the gas supply to the furnace. Measure the inlet gas pressure. Confirm the gas supply to the furnace is above the minimum required inlet pressure. Step 3. Shut off the gas supply and remove the gas manometer from the inlet pressure port and replace the inlet pressure port plug on the gas valve. Turn on the gas supply to the furnace. Step 4. Connect the gas manometer to the outlet pressure port on the gas valve and restore power to the furnace. Step 5. Call for heat. When the furnace has completed the calibration cycle, the furnace control will energize the direct spark igniter and will send 24 volts to the gas valve via the white wire via pin 5 of the gas valve. When the spark begins, check for 24 volts between pin 5 and pin 4 on the gas valve. Step 6. If voltage is present, the valve should open to allow gas to flow to the burner. Check for outlet pressure. If the voltage is present, but there is no gas outlet pressure, replace the gas valve. If there is outlet pressure, the burners should light. If the burners do not light, perform a direct spark igniter test. Step 7. If voltage is not present at the gas valve, allow the furnace to go into a retry cycle. Once the retry cycle energizes the direct spark igniter, check for 24 volts at the integrated control plug P7, pins 5 to 4. 24 volts should be present. If voltage is present, the problem is a loose connection between the integrated control board and the gas valve. If voltage is not present, replace the furnace control board.
We're going to go into the induced draft motor test. Since this is a 115 volt 3-phase inducer motor, it does test a little bit differently than what we're used to, as opposed to a single stage or a 2-stage. So it's important to understand how it operates and how to test it.
Induced draft blower motor test. Step 1. Shut off power to the furnace and ensure the inducer motor is securely plugged into the wiring harness connector. Step 2. Manually spin the inducer motor shaft and observe if the wheel spins freely. If it does not spin freely, Remove the inducer and check for obstructions in the housing. If the wheel spins freely, go to the next step. Step 3. Unplug the induced draft blower motor wiring harness. Step 4. The motor has 4 wires going to the plug, windings L1, L2, L3, and ground. Using an ohm meter, ohm out all combinations of motor windings, L1 to L2, L1 to L3, and L2 to L3. The resistance measured between all combinations of motor windings should be equal if the motor windings are good. If all of the readings are infinite ohms, the internal motor overload is open. Allow time for it to cool and reset. If any of the readings vary from other combinations, the motor is defective. Replace the motor. If everything checks out okay, continue to the next step. Step 5. Measure the resistance from L1, L2, and L3 windings to the green ground wire. The resistance should read infinite. If resistance is measured, the induced draft blower motor is shorted to ground. Replace the motor. Step 6. If the motor checks out okay, check the wiring from the motor to the integrated furnace control. If the motor will still not run, replace the integrated furnace control.
Okay, we'll go on here to the video on testing direct spark circuit. This was pretty good. We discussed it a little bit yesterday in the first part. This particular video will show you how to test the direct spark circuit, and this is pretty much across the board on all Rheem spark circuit control boards.
Testing direct spark circuit. Step 1. Ohm out the spark igniter and wire assembly from the tip of the spark rod to the wiring connector that attaches to the furnace control board. The ohms should be 0 ohms. If the igniter ohms out infinite, replace the igniter assembly and wire. If the igniter assembly checks out okay, proceed to the next step. Step 2. Remove power to the furnace. Step 3. Attach a length of 12 AWG wire to a ground screw on the furnace cabinet. Step 4. Remove the spark igniter wire from the high tension terminal on the furnace control. Step 5. Strip a short section of wire insulation from the loose end of the 12 AWG wire. Step 6. Turn on power and call for heat. Step 7. Using needle nose pliers with insulated handles, hold the stripped wire end about 1/4 inch from the furnace control spark igniter terminal. When the furnace enters a trial for ignition, the high voltage should spark from the terminal board to the end of the wire. If it does, check the burners for a good ground. If the furnace control board does not generate spark, replace the furnace control.
So that's a pretty foolproof way to check and test the boards. Like I said, that's an important, to me, it's a very important thing to know, because if you're out in the field and you're unsure, you certainly don't want to test them with a meter. And for me, the last thing I want to do is go buy a part that I may not need. Okay, so we'll get in here next to the ECM motor module and windings test. Like I say, if you're out there in the field, hopefully you have an ECM motor tester now. There's different ones. Zebra makes some pretty nice ones. Gentech makes them, as well as Supco. The best ones to get are the ones that have both harnesses, the old 16-pin, and then also the newer style with the 4-pin connections. If you have those, it makes motor testing so much easier, so much less time consuming, and you're really not guessing at that point. So we'll get into this video here.
ECM motor module and winding test. Warning: always disconnect the power from the HVAC system and wait at least 5 minutes before opening the motor, removing the 2 bolts from the motor control end belt, and or disconnecting the 3-pin plug to the motor. This is to allow the capacitors to dissipate for safety. Step 1. End any calls for furnace operation. Shut off power to the furnace. Step 2. Remove the bottom furnace panel to gain access to the blower motor. Step 3. Unplug the 4-pin connector at the ECM motor. This connector is the motor end of the harness that leads to the furnace circuit board plug P5. Step 4. Plug the 4-pin Tech Inspect tool plug into the ECM motor. Step 5. Connect the low voltage Tech Inspect clips to 24-volt power. Step 6. Restore power to the furnace. The Tech Inspect tool light should be lit. Step 7. Push the button on the Tech Inspect tool. After a brief delay, the blower motor should run. If the motor does run, the problem is either an open circuit in the motor harness leading to the furnace control board plug P5, or the furnace control board is defective. Repair or replace. If the motor does not run, continue on to the next step. Step 8. Remove power to the furnace and remove the screws that secure the blower motor to the furnace cabinet. Slide out the blower assembly. Step 9. Remove the 2 screws that hold the blower motor module to the blower motor. Step 10. Unplug the blower motor from the module. Set the module aside. Step 11. Using an ohm meter, ohm out the motor windings of pins 1 to 2, 2 to 3, and 1 to 3. Resistance should be within 10% across all combinations of motor windings. If the windings are all infinite ohms, allow time for the internal overload of the motor to cool. Recheck the ohms after the motor has cooled. If any combination of windings exceed 10% of the others or reads infinite ohms, the motor is defective. Replace both the motor and module. If the motor checks out okay, continue to the next step. Step 12. Measure for electrical resistance between each motor lead and the end plate of the motor. There should be infinite ohms between each motor lead to the chassis of the motor. If any motor lead to ground resistance reads below 100,000 ohms, replace the motor and the module. If the motor windings check out okay, go on to the next step. Step 13. Spin the blower shaft of the motor. If the motor spins freely and the motor windings check out okay, replace the module. If the motor does not spin freely, replace the motor and the module.
Okay, generally speaking, if it's under warranty, they're going to have you replace both the motor and the module, as it's a warranty issue. We'll go into the choke coil test. I mentioned this in part 1. You'll have what looks to be a very large transformer, which is the choke. You'll see this on 85, 100, and 115 volt or 115 volt BTU furnaces with the larger motor. So we'll go through this so you understand how to check a choke and how it operates.
Choke coil test. Step 1. Remove power to the furnace and disconnect the choke coil from the line voltage motor circuit plug PL-14. Step 2. Measure the resistance of the coil. Resistance should be measured. If resistance is measured, the coil is not open. If the resistance is infinite, replace the choke coil. If the ECM motor is not getting line voltage and the choke coil is good, the problem is either a loose connection at the line voltage 5-pin ECM motor plug or a loose connection at the furnace control board terminal L1.
So that's a pretty easy test. It's easy to identify. Like I said, if you have your 120 volts to the motor, then you know your choke is good. Okay, we'll get into this. Is a big one here. If you're verifying the communication signal, with other brands, they kept that kind of secret for years as far as what the communication voltage was. This video here will actually show you how to verify the communication signal from the board.
Verifying the communication signal. Step 1. With the system powered up but with thermostat off, check for a fluctuating DC voltage between E1 wire terminal 1 and C of the furnace. The voltage will vary between 2.5 to 3.5 volts DC. Step 2. Check for a fluctuating DC voltage between terminals 2 and C of the furnace. The voltage will vary between 0.3 to 1.8 volts DC. Step 3. The green and red LEDs of the furnace will flash to indicate when the unit is transmitting or receiving a signal. If the LEDs are not flashing, there is no communication between the furnace and the other components of the system. Check the wiring and connections. Step 4. If there is a loss of communication to the furnace, there will be a steady voltage of 2.7 volts DC on terminals 1 to C and 2.7 volts DC on terminals 2 to C. Between terminals 1 and 2, 0 volts DC will be present. Step 5. To confirm that the wired controller is trying to communicate, disconnect wires from terminals 1 and 2 of the furnace terminal block. Leave the 24 volts AC, RFC, connected to the wired controller. Check the wired controller to verify the communication signal is present. Wire 1 to C will have a fluctuating voltage between 2.5 to 3.5 volts DC. Wire 2 to C will have a voltage that will vary between 0.3 to 1.8 volts DC. If the voltage reading is not present, replace the wired controller. Step 6. The wired controller will display a communication error if a loss of communication is sensed.
That's very important to understand how to test and understand the DC voltage there. I get lots of people calling me about loss of communication. Typically, it's going to be I see it in the thermostat a lot if they don't strip enough wire back and they don't get it in there securely. It will initiate a communication error. Also, if they cross the E1, E2, if they cross those from the thermostat to the furnace, that's a guaranteed communication error. Or if there's a junction somewhere between the furnace and the thermostat or furnace and the outdoor unit, if you have corroded wires, poor junctions, that will also initiate a communication error. We'll do one last water test here. Video. This is on your water circuit test. We'll get lots of calls on those. To me, I think they're a fantastic safety circuit. They do serve their purpose. A lot of people don't understand exactly how they work, but this video here will show us how to test the water circuit.
Water circuit test. Step 1. Power furnace and call for heat. Step 2. Unplug lower water sensor pin and hold the pin to chassis of the furnace. The furnace should display a code 58. Step 3. Replace the lower pin and remove the upper pin. Hold the pin to the chassis of the furnace. The furnace should display a code 58. If the furnace displays the proper code, the sensors are working properly. Step 4. Replace the top pin and place furnace into normal operation. If the water sensors are not responding. Step 1. Call for heat and unplug the water sensor plug PL-4 at the integrated furnace control. Step 2. Check for a fluctuating 0 to 2 volts DC voltage between the two water sensor pins and integrated furnace control plug PL-4. If the voltage is not present, replace the furnace control board. Step 3. If voltage is present, check for and repair loose wiring connections between plug PL-4 and the water sensor. Step 4. Reattach the water sensor plug when testing is completed.
Okay, that's a series of videos, step-by-step test procedures. So we've covered some of the application, the installation, components, sequence of operations, various service procedures. So this will conclude part 2 of the Rheem modulating gas furnace course. I do appreciate you taking the time to attend. And in the chat feature there, I did put my name, my phone number, as well as my email. So feel free if you have any questions to give me a call anytime, send me an email. I'm more than happy to help you. So once again, thank you very much for attending.